And of course, tomorrow we'll take a look at some more practice. But let's get started with 3.44, which simply asks, for each pair of compounds below, identify the more acidic compound. Well, if you look at the first one, could anybody tell me which one would be the more acidic compound here? The alcohol or the thiol? Yeah, it's the thiol for sure, right? So we'll say this one is the more acidic. And if we think about areo, it's based on atom, because if we look at group 6A, we go from oxygen to sulfur to selenium to tellurium. Anyhow, as we go down, size increases, right? And the sulfur is going to better stabilize that negative charge, right? When we have the conjugate base, it's going to be much more content with that negative charge than the oxygen would be with the negative charge. All right, what about B? The first one, this is called phenol, right? And this one is called cyclohexanol. Don't get the two mixed up. They're very different compounds. Could anybody tell me which one of these would be more acidic? And it's not a trick. It's going to be the phenol, which is going to be more acidic, right? Because if we think about areo, right? The negative charge on both of these, if you draw the conjugate bases, that would result if you have this conjugate base on the phenol versus this conjugate base from the cyclohexanol. The negative charge is on an oxygen in both cases, so you can't use that. However, you can use resonance. There are no resonance contributors here, no resonance. Whereas for the phenol, we can draw 3 resonance contributors. I'm not going to draw them all because we spent a lot of time talking about resonance, but you should be able to draw the resonance contributors relatively quickly. So we have the negative charge here, right? And you should be able to keep pushing those electrons around, right? And draw out all of the remaining 3 resonance structures from there. Okay, let's take a look at the next two, which are 2 phenol derivatives. So this is C. We have this pentachlorophenol. So you have the phenol, and I'll just copy and paste it since I have to draw it again. So copy and paste here. And on this one, we have all these chlorines. So there's one here. So this would be what, 2, 3, 4, 5, 6 pentachlorophenol is what that compound would be called. Anyhow, so we have these two. Could anybody tell me? Well, I guess you could probably figure this one out based on areo, right? If we think about the conjugate base that would be formed in each one of these cases, and maybe I should have circled this one here. Phenol is more acidic. If we think about the 2 conjugate bases that would be formed, so if we take these, let me copy them, we paste them down here. All right, if we think about the conjugate bases that would be formed, there we go. All right, you can't solve the problem based off of atom because the negative charge is on an oxygen in both cases. You can't solve it using resonance because they both have resonance structures. However, you can solve the problem using induction because this conjugate base has all the inductive electron withdrawing effects of all 5 of those chlorines. And so that one has the more stable conjugate base. So more, I'll put here, most stable conjugate base. And therefore, the one with all the chlorines on it is going to be a stronger acid. Let's take a look at D. D, in my opinion, is just a matter of knowing your pKa values, I think is the best way to do this one. So we look here versus, the acetylene, okay, which has a proton over here. Well, you should memorize that the pKa of an sp hybridized carbon-hydrogen bond is pKa is equal to 25, whereas the pKa of an amine is around 38. And so this one is going to be a stronger acid. For E, you have a carboxylic acid. this, and then you have a peroxy. This is called a peroxy carboxylic acid. So you add an extra oxygen in there like that. So can anybody tell me which one they think might be the strongest acid here? This one's called acetic acid. And again, you don't have to know the names, but I'm just kind of, this one's called peroxy acetic, son of a gun, peroxy acetic acid. All right, well, if you look at the conjugate bases of both of these, you know, if you're ever stuck, you can just use areo if you're not sure. And since we didn't look at peroxy acids, I'd say the areo is probably the only way we have to solve this one. And if we look at the two conjugate bases, so if we draw the conjugate bases here and here, well, if we think of areo, we can't use atom because the negative charge is on an oxygen in both cases, but we can use resonance, right? Because we can draw a resonance contributor here, but here there are no resonance contributors that we can draw, and therefore acetic acid is going to be the more acidic of the two. We look at F. So F, we have a ketone, and then we have an ether, like this. So we have this ether and the ketone. Again, this is one where I think the best way to do it would be to use table 3.1, right? You should know that the pK of an ether, or sorry, the pK of a proton and a ketone is 19, whereas all of these are just carbon hydrogen, you know, these are just sp3 carbon hydrogen bonds. So the pKs of all of these are going to be around, we'll put around 50. Okay, there might be some electron withdrawing effect here, but very little. And so this one is going to be the stronger acid. And there we go. We'll leave the last two for now, and I want to move on to question 3.46, which asks us to draw some curved arrows. Mr. Dion likes any question where you have to draw curved arrows. So 3.46, we'll start with A. We've got a reaction between this thiol. I'm going to make sure to draw all my bonds out here, and this alkoxide like this, and then we're given the equilibrium arrows. They actually give us the products, don't they? Right? I'd say you don't even need them. You know, you wouldn't have to be supplied to know that the alkoxide could pull that proton off. Should put my lone pairs on my sulfur like that, and there we go, like this. Maybe clean these up a little bit. Came out kind of funny, like that, and then we can draw the products. So we're going to be left over with the sulfur having a negative charge. We call that a thiolate. And then we're going to be left over with the alcohol like this. Well, how could we solve this? We could solve it using areo, or we could solve it using pKa values, because earlier on today I showed you that the pK of a thiol was around 7, and we know that the pK of an alcohol, it's around 16 to 18, and so the equilibrium is going to lie to the side of the weaker acid, so it's going to lie to this side, right? Remember that this is behaving as our acid, this is our base, this is our conjugate base, and this is our conjugate acid, like that. You could also use areo, right? If you think about areo and the atoms with the negative charge, well, we've got the negative charge on an oxygen and the negative charge on the sulfur. We can use atom, because oxygen, it goes oxygen, sulfur, selenium, tellurium, right? And we know that sulfur is bigger than oxygen, therefore it's going to be more stable, a more stable base, and therefore the equilibrium is going to lie to the side of the more stable base. All right, let's try one more for today. It's already getting pretty late. So yeah, let's try B. So this is another one where you'd really have to just use areo to solve it, in my opinion. So we have this interesting functional group, which is something we don't even look at. in Organic Chemistry 1, but we'll just leave it there, and I'll make sure to draw on all my bonds, and then we have the hydrosulfide. I'll draw the Lewis structure, so we have our equilibrium here. There we go, we have our sulfur. So we draw the conjugate base, and then we draw H2S. Like that. Well, we don't know the pKa value of this acid, so here we'd have to use Aereo. But we can draw the curved arrows, I think, pretty quickly. We have our base, which is going to remove the proton from the acid, and then this pair of electrons will go in here. So we have our base, and we have our acid. It's just fun to label these things. We have our conjugate base over here, and we have our conjugate acid over here. So if we compare the conjugate base and the base, right? And if we try to use Aereo to solve this in order to figure out which side the equilibrium is going to lie to, we can't use atom because the negative charge is on a sulfur in both cases. However, we can use resonance because there are no resonance contributors for this base. However, we do have a resonance contributor here, don't we? Right, this is going to be the more stable base, and so the equilibrium should lie to the side of the more stable base. And so we can just rewrite our reaction arrows and say that the equilibrium is going to lie to this side like that. And there you have it, my friends. We solved the first two problems, and I think that that's a pretty good start in some practice problems.